Mars has a north-south dichotomy. In other words, it's a distorted planet. Nature publishes 3 papers which attempt to explain this dichotomy, one of the oldest mysteries in planetary science.
I'll tell you, I'm thrilled about this because I've been working on this problem for over 20 years. And I started thinking about it in a very different place than where I'm at now. By Nature publishing this paper, it's going to give the problem a great deal of visibility.
Everything we observe on Mars happened since this event. And in many ways, this has really kind of defined Mars as a planet.
This investigation was produced using data sets from 2 spacecraft. The first was the Mars Global Surveyor spacecraft, which produced this topography model of Mars. And this was a spacecraft investigation that orbited Mars in the late 1990s. And the second data set that we've collected was gravity. The gravity was collected from the Mars Reconnaissance Orbiter spacecraft, which is orbiting Mars right now. I have a team of the best planetary gravity analysts on Earth, and they're also the best gravity analysts who study Mars. And Jeff was happy to get this data to analyze it.
So we've known for a long time that Mars has what we call a hemispheric dichotomy. So the northern half of the planet is at low elevation and is fairly smooth, whereas the southern half of the planet is much higher elevation, about 5 kilometers higher, and it's very heavily cratered. Now, the origin of this hemispheric dichotomy has been a real mystery in planetary science. It's one of the most ancient features on the planet, and you can see it completely dominates the topography of Mars.
Could this have been caused by massive volcanic activity and convection within the planet? Or could it have been caused by something from outside?
There are 2 theories of how it formed. One is that through mantle convection, one side of the planet, the crust got thinned, while in the other it got thickened. And another explanation that was proposed was that a very large impact effectively excavated part of the planet, leaving this thinner crust in the north.
What we did was set out to test the hypothesis that a single large event could redistribute crust globally from the northern hemisphere to the southern hemisphere, leaving behind a morphology of a basin that's similar to what we see today.
Their mathematics simulates a momentous event some 4 billion years ago.
This idea of a very large impact, testing it via numerical simulations using a technique called smooth particle hydrodynamic, where you represent the planet as collections of particles, was first proposed to me when I was a graduate student at Cornell by Professor Steve Squires. I tried to do this and failed because at the time computers weren't fast enough to properly simulate this event. When Margarita showed up here at Caltech, she took this idea and ran simulations on a very large computer downstairs called Cetera, dedicated to understanding geophysical problems on the Earth and other planets.
A lot of the work that was involved in this project was looking at a very large parameter space, looking at different impact energies, impact velocities, and impact angles, and then looking at the simulation results and seeing whether the features that are produced by these impacts are consistent with what we see on Mars.
I was a skeptic about the dichotomy being due to an impact, but for a good reason. We produced a topographic model for Mars, which is illustrated in this globe. Blue corresponds to low elevations. And so here, blue is not water, blue is low. And if you look at the outline here, no matter how you orient it, you don't get a round structure. In the solar system, most impact craters are round, and the dichotomy boundary on Mars was just not round.
The conventional wisdom is that the impact events act as an explosion, with the exception of only the most oblique events that are depicted in these experimental images here. Most impact craters actually exhibit a circular cavity. What we found through these numerical simulations is that for very large impacts, the distribution of ejecta and the remaining cavity have an elliptical geometry, very consistent with the results that were obtained from data by Andrews Hanna et al. At MIT.
Jeff came along and we started looking at the crustal thickness, and there was the issue of this province right here. Is a province called Tharsis, and Tharsis is a large volcanic region. It takes up about a quarter of the surface area of the planet.
Both Tharsis and the Southern Highlands are shown by high topography. But if you could look beneath the surface, you see that the structure underneath the surface is very different. So if we look at the topography of Mars shown here, and as we unwrap the globe to a map of Mars, what we then do is we're going to remove this Tharsis region from the topography, and you can now trace the dichotomy boundary right across through the Tharsis province. So we can now, for the first time, trace the full globally continuous extent of the dichotomy boundary. Now, what surprised us originally is that the dichotomy boundary follows a fairly smooth path around the planet. It doesn't look at all irregular. And when we looked into this in more detail, what we found is that this path is actually the projection of an ellipse onto a sphere. And if we take this flat map and we collapse it back onto a globe, now we can see how the dichotomy boundary looked before Tharsis on this spherical planet. And it still looks irregular, but if we now take this globe and then we reorient it so that we're looking at the center of this lowlands basin, and now just unwrap the planet. So we flatten it out, but this time in a polar projection, centered on the center of this lowlands basin, you can see this elliptical shape quite clearly.
Well, this changes the ballgame. Elliptical craters only occur with very, very low-angle impacts, essentially nearly horizontal, so less than 10 degrees from the vertical. And I think that an impact origin for the dichotomy of Mars is now the simplest explanation. And when I look for explanations, I like simple explanations when I can find them, and that's what I like about this.
To properly simulate an off-axis impact, one needs to execute the simulation in 3 dimensions. This is very computationally expensive, and to do that, we require a very large computer, where with 4,000 processors, we can simultaneously explore many different initial conditions in 3 dimensions with a very large number of particles that represent Mars. What you're seeing on the screen are the results of one of our impact simulations, showing the results of an impact event that is compatible with the observations. In particular, the color of the particles, which represents the internal energy of the material, a proxy for its temperature. Some of the ejecta falls back onto Mars. Another part of the ejecta goes into orbit around Mars. This is, in the case of the moon-forming event on the Earth, is what formed the moon. And finally, there's a small amount of material that actually escapes Mars's gravity with greater than escape velocity. A third paper appearing in this issue by Francis Nemo of UC Santa Cruz and colleagues considered the effects in very high-resolution simulations of head-on impacts in 2 dimensions. This is in contrast to the 3-dimensional simulations we execute here, where we consider the effects of oblique impacts, albeit at lower resolution.
This impact was essentially the defining event in the history of Mars. I mean, you're excavating not only the crust, but a significant amount of the mantle in nearly half of the planet. And that material is being launched out into space, and then it's landing on the rest of the planet. It's landing with enough energy that even just that material re-impacting the surface would have had a tremendous effect.
This impact shaped the current surface of Mars, and the lowlands of Mars then became the sink for anything that flows. And so water throughout the history of Mars would have flowed north. The Phoenix lander, in fact, landed in the high northern latitudes of Mars and has a robot arm which is attempting to dig beneath the surface to try to identify subsurface ice. And it's quite possible that the ice beneath the surface of Mars is ancient water that flowed there because of the fact that this impact occurred early in Martian history.
I think the take-home message is that the early solar system was just a really dangerous place to be a planet.